So in a transmission line, the input impedance seen at any length of transmission line is a complicated function of length, as we saw in the last video. This complicated relationship makes it difficult to analyze or synthesize transmission line based circuits and transmission line based systems. Thus, there is a need for a graphical way to think about this, to think about wave based phenomena. And specifically for microwave circuits, this was done by an engineer called Smith a long time ago. And although nowadays we don't really need any graphical calculation tools, we can simply use a computer to do this for us. The Smith chart gives you a lot of physical insight and intuition into the behavior of transmission line systems. And thus, it is a good thing to learn despite the availability of computers and other software. So the starting point for the Smith chart, understanding Smith chart, is to realize that the reflection coefficient at any point and the corresponding load, input impedance at that point, have a relationship which is given by this. So the gamma L at any point, so for here I am giving the example at the load terminal. For example, the gamma L at the load is equal to small zl minus 1 by small zl plus 1, where small zl is the normalized impedance. It is capital ZL divided by capital ZC. So for example, 100 ohm load would be 100 ohm load on a 50 ohm characteristic impedance line would be having a normalized impedance of 2, for instance. Although I have shown you the relationship here at the point at the load terminal, if you go at any other point along the transmission line, there the gamma will be a function of L, and the normalized input impedance at that point will also be a function of L. However, they will still be related by using this relationship. So gamma at any point L is equal to Z in or Z in, normalized Z in at L minus 1 by normalized Z in at L plus 1. So we can say gamma is equal to z minus 1 by small z minus 1 by small z plus 1, and where z is now the normalized input impedance at any point on the line, and gamma is the reflection coefficient at that point. Let us first prove that if I have a lossless line and passive load, then the mod gamma, the mod of the reflection coefficient of any reflection coefficient, is always going to be less than or equal to 1. We do this by taking gamma as z minus 1 by z plus 1, replace z, which is a complex number, by r plus jx. Here, the normalized ZL or z at any other input impedance as well, R is going to change from 0 to infinity, and R can range from 0 to infinity, and X can range from minus infinity to plus infinity. Substituting this, we see that mod gamma is given by R minus 1 squared plus X squared by R plus 1 squared plus X squared. And from this, X squared, this is always positive. R minus 1 is always smaller than R plus 1 for R greater than 0. And thus we can see that gamma, which is this complex number that reflection coefficient that we can observe at any point on the line, at any point on the line, it will always have an absolute value less than or equal to 1. Thus, graphically, we can represent gamma on the Argand plane, and we can say that it lies within the unit circle in the Argand plane. So any and all possible values of gamma are always going to lie within this Argand plane. And some points you can notice, the gamma 1 plus J0 results from an open circuit, gamma minus 1 plus J0 results from a short circuit, and the gamma of 0, comma minus 1 or 0, comma 1, for instance, is going to result from having some purely reactive impedance. The VSWR for a line is given by 1 plus mod gamma by 1 minus mod gamma, and this is a property of the line itself. So this is going to be same everywhere on a line terminated with a given load. Gamma at any point L is given by gamma sub L e to the power minus J2 beta L, and immediately you can see that the absolute value of gamma at any point L is same as its value at the load. Thus, all the gammas possible for any given load are going to lie on a circle. And that circle is called the VSWR circle, as we can see in the Argand plane. Remember, all this is still in the Argand plane. If you consider a line, transmission line with load at AB and the generator and at CD, for instance, the gamma at AB and the gamma at CD are going to both lie on the VSWR circle, and the distance between them in terms of angle, in terms of the gamma 0 and gamma L, have different angles. The difference in angle between them is given by 2 beta L. And because gamma L is e to the power minus J2 beta L, you need to go counterclockwise in order to reach CD from AB. So we have a few things now in the Argand plane. We have the concept of a VSWR circle, and we know that AB, any terminal AB or a terminal at another point CD on the line, they are going to lie on that VSWR circle, and how you go from one point to the other point is by rotating, moving along the VSWR circle. If you go clockwise, you are basically going towards the generator, and if you're going counterclockwise, you're going away from the generator and towards the load. This is what I've shown here. So we can locate different reflection coefficients. Also, we can transfer reflection coefficients from one point to another point on the line, either towards the load or towards the generator. So anytime you're using this chart in your mind, you should imagine that you're really walking from one terminal to the other terminal, which makes it easier to use a Smith chart. In the actual Smith chart itself, there is no scale for gamma. So gamma has to be read in the polar form. So if I tell you the gamma is 0.5 angle 30, you can locate that. But if I say it's 0.5 plus j 0.5, you need to first convert it into polar form before locating it on the gamma circle. This is great. So we can now represent all possible gammas on the circle, but this is only half the battle. It's useful if we can also find the R and X values for any given reflection coefficient. How do we do that? So that is a somewhat lengthy derivation. So I'm going to go over it pretty quickly. I'm going to show you how it is done. Basically, we start with the relationship between z and gamma, and basically z you can express as 1 plus gamma divided by 1 minus gamma. Remember, gamma was z minus 1 by z plus 1, and from there we get z is 1 plus gamma by 1 minus gamma. Gamma is a complex number, so I'm going to replace gamma with a real gamma r plus j gamma I, and expand out z as r plus jx, and I'm going to now get proceed with the simplification of this by making the denominator into a real number by multiplying with certain factors. And after doing all this, and you can see this derivation, we're going to end up with this equation, where all I've done here is simply converted the denominator into a real number. We get some relationship between r plus jx on one hand and gamma I and gamma r, an expression involving gamma I and gamma r on the other hand. This is an equation in complex numbers, so this spits out two equations. So you can separately equate the real and imaginary parts of this equation to give you two separate equations. And I have done all that, and I get two separate equations. In the first equation, I will have terms involving gamma I, gamma r, and little r. In the second equation, I'll have terms involving gamma I, gamma r, and small x. How do we interpret this? So remember, we are on the Argand plane and the gamma circle. So gamma r and gamma I, if I give you an equation in gamma I and gamma r, that is going to give you some sort of a parametric curve. And in this case, it turns out that these are going to be circles whose parameters, the circles or the parameters of the circle are center, coordinates, and the radii. Those will depend now upon the parameter in the first set of curves on little r. The second set of curves, it's going to depend on little x. So that's why these two are parametric curves. Physically, what they are telling you is, if I have a load with a given value of resistance r and any possible value of reactance. So r is a constant, the resistance of the load is constant, reactance can be any value. This is a set of loads, and this, for each of the loads in this particular set, I'm going to have a corresponding gamma. What the parametric curves 1 is telling you is, it is collecting all the locus of all the gamma values that you will obtain for loads of the form r plus j anything. And similarly, the second set of parametric curves is telling you the locus of all gamma points that you can obtain with a fixed value of reactance. So it can be anything plus j fixed reactance, for example. So that is how we derive these equations, and you can further simplify. Basically, what we do in the first equation then is, we are going to start collecting terms in gamma r together, then we're going to start collecting terms in gamma I, and then we're going to leave all the terms, constant terms on the other side. After doing all this, you're going to end up with this equation. Notice that this equation only has gamma r and gamma I terms and r terms, right? It only depends on the resistance value. And you can identify, of course, that this is the equation of a circle. with center at r by r plus 1 comma 0 and a radius of 1 by 1 upon r. A similar derivation with the second set of parametric curves results in this equation, which also turns out to be a circle. This circle has a center at 1 comma 1 by x, and it has a radius of 1 by x. So we end up with this. To summarize, set the parametric curves of type 1 have center at r by r plus 1 comma 0, radius at 1 by 1 plus r, and type 2 has center at 1 comma 1 by x and radius of 1 by x. Let us quickly see what these loci look like. So the first set of circles, the R circles, just take some examples. Here I've taken 5 examples. If I take 0, center will be at 0 comma 0, radius will be 1, which is the unit circle as I've marked here. If I take r as infinity, center is going to be at 1 comma 0, and radius is going to be 0, 1 by infinity, and that is simply the point 1 comma 0. The value of r equal to 1 gives me the circle that is having a center of 0.5 comma 0, and it has a radius of 0.5. Any value of r between 0 and 1 will give you circles like the green circle. It's going to lie between the r is 0 circle and the r is 1 circle. And any circle that has r greater than 1 less than infinity will lie between the r is 1 circle and r is infinity circle. These are the purple curves that we see. Notice all these circles, the centers of all these circles lies on the real line. And all these circles pass through the point 1 comma 0. Why is that? In all cases, I have a load, let's say 1 plus j infinity or 0.5 plus j infinity. I always have that case, right? Something plus j infinity. Loads with infinite reactance but finite resistance. All those loads will be open circuits. Their reflection coefficient will be 1 comma 0. And so all these R circles, constant R circles, must pass through 1 comma 0 point, must pass through the open circuit point. Similarly, the other thing we notice is that the other thing we notice is obviously that it's symmetrical. So all the centers lie on the real line. Now we can do a similar thing with the X circles. Taking the special case of 0 gives me a center at 1 comma infinity and radius of infinity. Now an infinite circle is basically like a straight line, right? And in addition, notice two things, that if I fix the reactance at 0, then I could have the case 0 plus j0, could have a short circuit, which means that this circle, x equal to 0 circle, must also pass through the short circuit point, minus 1 comma 0. Similarly, I can have a load infinite plus j0. So it should also pass through the open circuit point. So we have a circle that looks like a line, and it passes through both the short circuit point and the open circuit point. Thus, we know that it must be just a real line, right? The actual circle will go outside the outside the unit circle. All those points are not of interest because we are only concerned with passive loads here, and all the final gamma values must lie within the unit circle. This is my unit circle, and I'm simply showing you how the X circles look like for different values. And we're going to only consider those arcs which lie within the unit circle. This is the x equal to 1 line, by the way. Yes. Okay, So if I next consider x equal to minus infinity, then obviously that's the open circuit point, and that should be just the 1, 0 point on the unit circle. It's just the open circuit point. Any other value in between, for instance, x equal to 1, has a center at 1, 1 and radius of 1. And those are the ones, this is the x equal to 1 circle that I've drawn here. This is the x equal to minus 1 circle. And you see the portion of these kind of circles that is lying within the unit circle look like that, right? They look like that basically. And we know where is x equal to 0 circle, where is the infinity circle, where is x equal to 1 circle, and similarly you can locate the other points as well. Now that we have an idea what the circles look like, let us next go to the real Smith chart and try to orient ourselves based on what all we have learned. The first set of annotations here that I've shown you the full chart. First, we identify the big red circle, that is the bounds of our gamma. Only within that is things that we are interested in. Outside that, here you see there are 4 different scales. These scales allow you to locate a particular value of gamma, and also it allows you to move in the transmission line either towards the load or towards the generator. So let me first show you scale number 3, and you can see here it says angle of the reflection coefficient. So this is where you will be able to read the angles. So 30, 20 for example. So if I tell you the gamma has an angle of 30, you know that it lies on this line. Next, we need to find the magnitude. Let us say I say the magnitude is 0.5. How do we find the magnitude? We know that from here to here, the value is 1, right? So at this point, gamma has a value of 1. So 1, 30 is here. And so 0.5 must lie somewhere here, right? So there is an exact scale to do this. That is scale number 3 here. Reflection coefficient E. And you can simply use a divider or a scale and you can measure off exactly 0.5 or whatever magnitude of mod gamma you have. So this is how we locate any gamma, and how do we go from one point on the line? If I add to another point on the line, we have to draw the VSWR circle and move. If you are moving towards the generator, we need to use the scale, the first outermost scale. As you can see here, it goes in the clockwise direction, as we saw earlier. This is the clockwise direction for towards the generator, and you can see the scale. It's given in terms of wavelengths. If you recall, everything repeats on the transmission line with half a lambda period, so we don't really need to go anything further than a half a lambda. So these scales go from 0.0, they go when you come back, you have done 0.5 lambdas basically. So 0, 0, and you can see here 0.49. So 0.0 is same as 0.5. This is how you read distances on the Smith chart. If you want to go towards the load, that is a counterclockwise motion. That is also seen in the scale number 3. So this is how we can locate any gamma, and we can move back and forth on the line as well. There are many other things that we can see on this chart. You can measure SWR, transmission coefficient, and so many other things as well that you can explore here. I'm not going to go into that. Finally, I want to look at the impedance Smith chart, and let us now look at all the R and X circles that we just encountered. As you can see here, the R circles are given by this scale here. So R equal to 0.5, 0.1 circle, for example, passes through this point, and it's also going to pass through 1 comma 0, right? So if I say r is that, your point is going to lie on this circle. Or given any point, we can, for example, if I give you this point, you try to see which r circle it lies on. Do you know what is its? For example, this particular purple point lies on the 0.5 r equal to 0.5 circle. So I know that the value of r here is 0.5. Now, the x circles are also given here, and the x circle scale is given here. Inductance component. So this is plus x circles, x equal to plus something circles, and x equal to minus something circles are given in the lower hemicycle. So for instance, our purple point here, which x circle does it lie on? As we can see here, it lies on the x equal to plus 1.0 circle. And so our purple point has an impedance, normalized impedance of 0.5 plus j 1.0. This is how you can locate the z values for any point, and also how you can locate the gamma for that same point. However, in electrical engineering or in any circuit design, sometimes we have parallel loads. So just having a series impedance calculation is not enough. We also need some admittance calculations also sometimes, especially when we have parallel connections. So how do we find out the admittance of any given point? To do that, you need to first realize the properties of the lambda by 4 transformer. This is basically just a line that has a length of lambda by 4. And if you go through the formulae, you can realize one thing, that the z measured here at the distance of lambda by 4 and the load, they have a dual relationship. If the load value is normalized load value is little zl, the zin measured at lambda by 4 is going to be the reciprocal of that. Or equivalently, what we can say is that the admittance of the input admittance measured at the end of a lambda by 4 transformer is same as the impedance of the load. So this construction allows you to see this. If I consider the r equal to r dash circle, and if we consider points that are diametrically opposite. Why diametrically opposite? Remember, if I need to go lambda by 4, if I complete one circle on the transmission line, I'm going to reach a distance of lambda by 2. So if I complete half a rotation, or which is same as going to the diametrically opposite point, I'm going to achieve lambda by 4 translation. So using these two ideas, we can realize that if the black circle is r equal to r dash circle, the red circle is nothing but the g equal to r dash circle. So the red circle here, g equal to r dash circle, collects the locus of all admittances, collects the gamma that can be obtained by all the loads whose admittance has a susceptance of r dash. Sorry, conductance of r dash, not susceptance, conductance of r dash. In a similar way, we can also realize that the x equal to x dash circle, for instance, has the diametrically opposite of that gives you the b, the susceptance equal to x dash circle. Okay. So what we realize is that the impedance Smith chart and the admittance Smith chart are nothing but mirror images of each other. Um, However, notice that we should not move the open circuit and short circuit points. They will stay the same. The only thing that is different between an impedance chart and an admittance chart is in how we read the values of admittance or impedance. It is still the Argand plane, it is still the Argand plane for gamma. So gamma will be measured in exactly the same way in both the charts. You can use the normal Smith chart turned upside down to do calculations, or you can also find on the web admittance charts, specially printed admittance charts. Whatever is comfortable for you to do your calculations in. I just want to mention very quickly where we will use Smith charts. If you have slotted lines, slotted line measurement problems, for instance, and also in impedance matching, creating impedance match circuits and so on, we can also use it in ensuring maximum power transfer or optimize power transfer and such examples. This will be given in a separate video, and I'm going to conclude this video. Thank you very much.